Hi, everyone. It's my pleasure to be at IAA today. I'm going to talk to you guys about building self-driving cars safely. And first, I want to talk to you guys about the journey it takes to get to full self-driving. There's a lot of AI that you need to build self-driving technology, and to do it safely requires a lot of expertise from cloud to car. So first, deep learning really started with AlexNet a little over 10 years ago. And what we did was, researchers built a convolutional neural network, trained it on GPUs with a lot of data, and they realized you can do really good image classification with these networks. And then a lot of research focus and developer focus moved to understanding the world with perception. So we went a little bit multimodal. It was no longer just images. You added sort of audio and text. And you actually had the ability to have a world model of what you were seeing and understand it a little bit. So a lot of enhancement in perception. The big leap actually came with generative AI with ChatGPT just a few years ago, where essentially large language models were being developed, and you were generating. So you weren't just understanding the text, but you could generate an answer. You can also generate images as part of the answer. And that created a lot of disruptive experiences that we could take advantage of to build great products for all of us. Once we had that, we shifted over to agentic AI. And there, the algorithms that we could build to sort of be able to think were different. We could actually take a problem, break it out into individual pieces, so essentially perceive and actually start to think, what's the right type of solution to this problem, break out the problem into pieces, think through the best option, and come up with the best solution. That created these digital assistants, right? So, a customer service agent, or just, your concierge that can answer your questions and give you recommendations. From there, now we're moving to physical AI, and that's what my talk is going to be focused on. So we're now talking about robotics, right? Like, you're physically moving. You're not just understanding and answering questions, but you actually have to make an action. And when you have that type of a product, there's extra rigor in how we think about safety, because we can't ever cause damage. We can't cause an accident. And so today I'm going to talk about all the innovation, all the work you need to do to build physical AI safely and securely. Okay, so first, within NVIDIA, actually, automotive is a huge vertical. And most of the time when we talk, sometimes people ask me questions. They say they ask me questions about like Qualcomm or Mobileye. So they're talking about inside the car. That's just a very small sliver of what NVIDIA does. The in-car computer is less than half of our automotive business. Most of our focus is on how we help customers train models in the cloud, how we help people simulate an autonomous driving software, test it, validate it, put it in the car, and have a data loop that's super efficient from cloud to car. But we also help our partners in automotive actually design their cars. So we build AI-accelerated digital twins that help you design a car real time. We also help our partners simulate their factories. Before you build a factory, you have to think through what's the most efficient way to build the assembly line. And you can't just build it and then make changes. It'll be super expensive. So you actually want to have a digital twin created of what a factory is, and design it and test it to be as efficient and productive as possible. And then you build that car, that factory. And then finally, in the enterprise, every type of company, but especially in enterprise, for automotive, you're thinking about how to recreate how your company acts to be more efficient using AI. So is there an easy way for me to have customer service for my employees and my customers? Is there a faster way for me to develop products? Can I take all this data I have access to and make better decisions? So we help our customers with that as well. I'm going to focus on just the in-car today, but in automotive in NVIDIA is super large, and we do a lot more than what I'm going to talk about today. Okay, so within the self-driving cars, to solve this problem, you actually need 3 computers. So, and software running on each of these computers that's super rich in AI. So, first you need a computer that runs the algorithms in the car, so the inference in-car computer. And it needs to be really good at doing inference and AI efficiently and safely. The algorithms running in that car are next generation models that are end-to-end, and they also have to have a safety sort of guardrail stack that runs side by side with it. Then in the cloud, we get a bunch of data. We need to be able to train this data efficiently. We need to be able to label it automatically. Otherwise, it'd be so expensive I had to manually label data that I'm getting from these cars. And we need to be able to then test our AV software in simulation first and then in car. And how we test that software, we have to add new scenarios. And so we need a world foundation model to create the scenarios that we don't see in the real world and then be able to test it. There's so much AI software and expertise, and what I would tell you guys is the companies who are best are the ones who have a loop from the cloud to the car that's most efficient. And so usually you hear people say, tell me about the drive. How many miles did you drive without a disengagement? That's super important. But key metrics should actually be, how long did it take us to take this data and process it? How long did it take me to find an issue in my drive, root cause it, and fix it? How long does it actually take me to train a model? I have data, how long does it take me to train the model? Those are actually important metrics to tell you how good your AV team is, AV as an autonomous driving team is, to be able to build safe autonomous driving products. So, I want to talk about long tails because this is the essence of why autonomous driving is super hard. You can't actually come across real-world data that is reflective of every type of corner case that you're going to see. It's just too rare. It just really is. Like, maybe I've seen someone's suitcase that fell on the road, and I needed to know how to handle that if I had a self-driving car. But maybe someone else had a different random scenario. There's a mattress, certain type of animal, or sometimes cars have a bunch of things on the top of them, and it actually doesn't look like a car. You need to be able to recognize all of this, and saying that I'm just going to have that data in the real world is absolutely not possible. It'll be way too costly to get enough real-world data to cover all these long tails. And then it's not just that scenario, but you need that scenario with infinite variety. You need it at night, you need it in snow, you need it when it's cloudy, you need it when it's rainy. You need so many scenarios. Real-world data doesn't handle it. So actually, if you want to have a data strategy, you need to actually have 3 core pieces of technology. When you have cars that are in production on the road, you need to have special AI software in the car that takes those long-tail events that you come across and captures it in the car so you can send it in the cloud. And that's AI, because if I took all the data that my fleet of cars was collecting, it would be way too costly. I actually need to take a fraction of a % of data. But when it's a long-tail type of scenario, you want to capture it and you want to send it to the cloud. Second thing is you actually need the ability, every time you're driving, when you have an issue, you need to be able to take that issue from the car, reconstruct it, get it into sim, and then add variety to what you reconstruct and get to sim. That engine, that flywheel also needs to be world-class. And finally, you need a synthetic data generation engine so that when you can't find those long tails, you can actually create them in simulation. That data should be physically accurate, so when you actually want to test your AV or train your model, actually it performs just like real-world data, and your software gets better. You need all 3 of those things to have a good data strategy. Okay, so I'm going to show you guys the data flywheel, and the rest of this presentation is going to talk about all the pieces of software and services that NVIDIA offers to help our partners in automotive build self-driving cars better, faster, more efficiently. So, I talked about data already, right? So you're going to collect data from cars, and you're also going to generate synthetic data. So you need a world-class synthetic data generation engine. Once you have those 2 sources of data, models now are trained on video. It's no longer like AlexNet that I was talking to you guys about, where you're taking images and you're training on that. You're training on like 30 seconds of video because you need memory context. I might pass a traffic light and be stuck for 15 seconds past that traffic light, I actually have to have context where I am and what I'm doing. If I don't have memory as a self-driving car, I could cause an accident. So we need long clips of data. When you have that much data, you need a way to efficiently process that data, automatically label it. So we have some partners who have 3,000 labelers, and they're manually labeling data from the car. You cannot do that when you're trying to build a next generation model. A large language model, a video language action model for self-driving. So you need a fully automated data processing engine. We actually have built it, and we give it to our customers. Because we're building the full AV stack, so if a customer actually wants raw data, gets a bunch of raw data, and they want it to be annotated, curated, so that then they can find the data they want, we've built that engine, and we offer it to our customers as part of a Cosmos and Omniverse pipeline that we have. Once you have that, though, you have a scenario where now you want to find those long tails, so you need to be able to create that synthetic data. And so we've built a world foundation model for creating data, and that helps you then have a robust test infrastructure. So I'm going to go through all of these in detail, and then, of course, you put it in the car, and you need to make sure the in-car computer is super high performance and safe, so that we never make an unsafe decision. Okay, so the first thing that we do, which is super helpful, is we have a model that we have built. It's a world foundation model called Cosmos Predict. What does this do? It takes sensor input in from the car, camera as an example, or LiDAR or text, and it actually generates the trajectory output of the car, and it's also generating the trajectory output of all the other actors on the road. That is the essence of what a world foundation model is, right? It takes all the input and it says, this is the safest action for the car to take. So we give this to our partners, open source, and our partners can then take that source code, fine-tune it on their own data, so essentially do post-training on that data, and then they can optimize it on the computer they have on their choice. In addition to that, so that model can run on the cloud. You can train it on the cloud. It also runs in the car. Cosmos Transfer is another model that we've created that's also available in open source that essentially lets you take all the sensor inputs from the car, the camera, the LiDAR. You can also take map information that you have from the car, semantic map information, and you can use that to actually create the data in SIM that is photorealistic. It's essentially exactly the real data that you captured. And then you can take that photorealistic video, and then you can permutate it. You could say, you know what, give me that scene, but at night. Give me that scene when it's snowing, when it's raining. Now you have the ability to capture these scenarios that are super rare and actually add those, the other part of it, which is, it could be a hard scenario, but then what about at night? What about when it's snowing? Cosmos Transfer lets you do that. So now you can take limited data that you captured in the real world and generate much more with more variety that you need to build a safe AV. Cosmos Reason is another super important model. So you remember I talked to you guys about generative AI, agentic AI, and I said agentic AI gives you the ability to reason. It breaks apart a problem into multiple steps, and it actually reasons through what's the best action I could take of these multiple possibilities. It's essentially like doing math. You break it into its numerous pieces, you think through what's the best way to solve it, and then you solve it. You need a reasoning model. You need a vision language action model that has chain of thought reasoning. So if you have a core model like Predict, and then you add a Cosmos Reason head to it, now you have a reasoning chain of thought capable model for self-driving. It's super foundational and important. But it's also important for other reasons. It's not just drives better, but I actually think that if I have the ability to understand why the car took an action, a reasoning model actually tells you why it did something. So now if I'm in the car and I'm slowing down, if the car is slowing down, the car can actually tell you, hey, I'm slowing down because of the lady crossing the intersection with her baby. The reasoning model actually tells you why it did it. So now inside the car, you can actually have user experience feedback that the car is telling you, why did it slow down? On top of that, in infrastructure, Cosmos Reason can be used to take data and caption it. It can actually tell you, hey, this data is a fork, is a merge. And so when we actually want to have a data factory, we want to be able to curate data. And we can curate data on how Cosmos Reason captioned the data. Super important to be able to search and find the data that you need quickly. And so Cosmos Reason is also very effective in infrastructure. Okay, so I'm going to try to kind of put all of these together here. So, we talked about you have the special scenario recorder data in the car that collects maybe less than 1% of the data. That's super important. And then I said you need to be able to then synthetically generate the data. So this is a good summary of it. Maybe you have 1,000 miles of really valuable data. But then what you want to do is you want to take the scenarios that you've captured from real life and you want to do behavior permutations. So think of it as you're handling an intersection left, but then you say, I want more pedestrians crossing when I'm doing this left. So we add pedestrians to the scenario that we already captured. Or I want more cars. I actually want it to be more congested in this scenario. So the core data set that we had, we've just amplified it with more variety. That's super critical to have autonomous driving software that can always be safe. Then sometimes we actually want, it's not we're adding behaviors, we want to add something to what we captured. So for example, we might say, I want to add a certain kind of truck to this intersection because I want to see how I can go around this truck. I want to actually add a parked car on the road, and I want to see if I can nudge around the parked car. Well, a really world-class synthetic data generation engine can also do that, and we have that capability. We give it to our partners. Then you have Cosmos permutations, which I talked about earlier. It's Cosmos transfer. We have these scenes. We've permutated the behaviors. We've permutated the type of actors on the road. And then we say, now let's do it for night. Let's do it with snow. Let's do it with rain. So essentially now, somehow we took 1,000 hours of really valuable data, and we've turned it into 1 million hours of really valuable data. And then you start to feel like your AV is super intelligent. Now, when you take that, it's super important, but also you also need that reasoning model. Why is the reasoning model important that I just talked about in the previous slide? A reasoning model thinks of what it's seeing, and it actually can make an intelligent decision even if it never saw it before. You also need that because even with the synthetic data generation pipeline I talked about, you can't always handle everything, so you need a reasoning model in your self-driving car as well. Okay, I kind of talked to you guys about this before, but you're going to have all this data. You need to be able to intelligently query it and search it. So you actually need a world foundation model. You need an intelligent model that can look at a video and actually find you exactly what you want. Our AV engineers have a problem on a fork or a merge. You know what they do? They say, show me all the scenes with fork merges with like this kind of situation. And if you have an intelligent search engine in your infrastructure, you actually just go find all those scenes and you can train the model immediately. If you actually had to manually go find that, that would be weeks or months of work. With Cosmos Video Dataset Search, you could just immediately do a query, find all those clips, and train your model on exactly what you're looking for. Okay, so the next important piece of technology you need is every time we're driving in the real world and we're trying to build a self-driving car that's safe, we're going to have an accident. We're going to have a problem. It's a disengagement or it's an uncomfortable event. What we want to be able to do is take that recorded log data and actually be able to recreate it in simulation exactly like your recorded log data. And then the first thing you want to do is you want to root cause what the issue is, fix your AV software for that issue, and then you want to replay your fixed software on exactly that issue and see if you fixed it. That's the development flow that you need, and we have that capability with neural reconstruction engine that we have within our pipeline. And then with what we talked about earlier, you can then take that scenario that you failed and you can amplify it with the synthetic data generation that we talked about earlier. So this actually kind of shows you what we do, and every autonomous driving company needs to do. You have an issue, and you capture that log, you take it into sim, and you reconstruct it. And now it's running in sim. When we say sensor RTX, we've recreated that virtual car. It's running in sim, and I actually now have a fixed software for that issue. I test it, and I can immediately say, I've now fixed that issue, and I've proven it not just in exactly the scenario I failed, but I've added permutations. And we passed all those permutations as well. Okay, so we talked about all the things in infrastructure, the cloud computer and the simulation computer that you need to do. But in the car, the model also needs to be state of the art, and the models that you used to have in cars is completely being rewritten. Almost every car on the road today is using classical style DNNs. BEV transformers, fusion stack, planning stack. That's the way self-driving cars were architected for the last 5 years. The only exception to this is Tesla, which has an end-to-end model, and some companies in China today. So on the road today, these are the only examples of people using state-of-the-art AI in their cars. And that's why their cars actually drive the best. But you can't build that kind of software with chain of thought reasoning that we were talking about unless you have that infrastructure. How do you actually test a model that just takes sensor input in and gives you trajectory out? You can't. You actually need that neural reconstruction that I showed you on the previous slide. You need to be able to take a scenario, reconstruct it, test it in sim, and see if it passes. Then you know your end-to-end model is great. This kind of software is foundational for self-driving. If we take a standard large language model for video, so a video language action model, and we run it and just assess how effective it is, and then we add meta actions to it and chain of thought data, the performance of that model is twice as safe. It's significant. Now the thing is this kind of a model has two problems. One, it's very compute intensive. You need to be able to process these tokens per second super fast, right? Like you're going 80 miles per hour. You can't take too long to process what the sensor is seeing and be able to create an action. But when you have a chain of thought reasoning model, there's a second problem. You're thinking about what are all the permutations that I should consider before I decide what's the safest trajectory. So that's actually a different problem. It's like token generation. Token generation needs memory bandwidth efficiency. That's why Thor, which is our next computer, is based on Blackwell. And Blackwell has FP4 engine. At the essence, what's FP4 is it's able to process a vision language action model with chain of thought reasoning at twice the memory efficiency of a platform that maybe ran FP8, and then 4x the memory efficiency. That memory efficiency, how quickly you generate tokens, is super important to the experience of your self-driving car if you have a stack that's based on a vision language action model. So, I talked about our in-car computer Thor. Well, we have some exciting launches, at this, IAA. Mercedes is launching their GLC vehicle. Volvo just launched their ES90, and Lucid is launching their Gravity cars in Europe. We're super excited to be able to work with these partners. The next thing that you need within this cloud-to-car architecture to ensure your product is safe is safety methodology and know-how end-to-end. We call it NVIDIA Halos. So we have a whole bunch of tools, libraries, SDKs, software development process, simulation, infrastructure, software that makes sure that the software that you develop is built for automotive-grade safety and security. So we talked about physical AI. The car is going so fast, we can't ever make a mistake. Well, how do we build a system? Well, the first thing is when we design the system, we have to think about safety. So that means that it's great if my AI software is so good that I can run on camera, but you know what? Sometimes a camera can't see. It's dark, or something might have hit the windshield, and so the camera is blocked, or the sunlight is actually blinding the camera. So you actually want a separate sensor. You want the diversity of sensors. It's nice to have a radar and even a LiDAR in a car, because if the camera fails, you have something redundant. You think about your software architecture the same way. I want one way to see something, camera perception, but I want a different kind of camera perception algorithm so that if this algorithm didn't see it, I had another algorithm that did. And also you increase your confidence if they both agree. So we talk about design time guardrail. It's like architecting this system to be efficient. You designed it to be efficient. But then you want to make sure that your system is designed with runtime guardrails. Like you want monitors in your stack, in your computer that test what goes in and what goes out, make sure that there was no failure in your system. You actually want to have a safety guardrail or safety filters in your system. And then you want to have infrastructure pipeline that's built to automotive grade safety and security. What do I mean by that? We build a test for a lane change in self-driving. Well, we want to make sure that the test actually is correct. Just because we pass the test doesn't mean it's fine. So every feature, every function, every line of code needs to be tested, and the test needs to be ensured to actually be functional. Why do I do that? It's so much work. It's because we don't ever want to cause an accident. The investment in safety for autonomous driving is significant. NVIDIA alone has spent 15,000 man-years of engineers to be able to build this Halos methodologies and tools. And then we help our partners. We have all this learning and know-how. We give them the tools, we give them know-how, and we can actually assess what they did and give them feedback. Actually, NVIDIA now is licensed and certified to assess a partner stack. So just like TUVIS in Europe, NVIDIA actually has the know-how and the expertise to be able to say, I looked at how you built your self-driving code, and let me tell you how you should do it differently. Okay, so I'm also just want to say I'm super proud of one work our team did. We launched 3-4 months ago a functionally safe level 2+ stack that launched in Germany on Mercedes-Benz cars, and this stack will go worldwide. It's a huge body of work. Only Tesla has a stack that can drive any address to any address worldwide, other than NVIDIA. Super proud of that work. And then finally, the automotive ecosystem. We work with every automotive company. Everyone, and the reason is we work in the cloud, in simulation, and in car. And we're super proud that the companies that have the best AV, we work with Tesla to help them train their models in the cloud. We work with Waymo as well. We work with all the China NAVs, both in the car, in simulation, and in the cloud. But it's not just the OEMs, it's the software vendors. It's the ISVs. We take our software platform, we give it to the whole ecosystem, and then they can take that know-how and give it to their customers and partners. So we're super proud of the work, and thank you so much for your time.